While we're moving along, feel free to ask them as I'm talking, because I don't want you to feel like you need to wait until the end, because that's definitely not the point. So as Shivani mentioned, my name is Katie Ackerman, and I'm going to be talking about how we weather forecasts, an introduction to current practices and challenges of weather modeling. So just a little bit of a background about me. I'm a fifth-year PhD student in atmospheric sciences with Allison Nugent, and I study aerosol production. For those who don't know what aerosol are, they're just tiny particles that are suspended in the atmosphere. I study giant sea salt particles, which even though they're called giant, they're actually still very small. And I study their impacts on climate and clouds. At my heart, I'm an observationalist, but I really like utilizing models to explain the in situ observations that I gather. And I'm most interested in how we can use models to explain the natural phenomena around us. So just an outline of this tutorial. I will not be giving you a complete WRF tutorial. This slide is only 2 hours long, and I'm not even going to take that whole time because it would really just be very cut and dry, but the National Center for Atmospheric Research does a lovely tutorial that is a week long where you can learn how to do all of the things in WRF, or at least all the things in WRF needed to get you started. So I just want to be upfront and let you know that maybe at the end of this, you're not going to be able to run WRF, but you will have a good understanding of how the model works and what goes into the model, and potentially what are some potential things that can go wrong when you're modeling. So in general, I'll be talking about how we forecast weather, what WRF is and what it can do, as well as what are some of the extensions you can add to it that might be more specific for your research if you're not in atmospheric science. And then how does the model generally work? What are other available resources for WRF for you to learn on your own? And then what are the current challenges that exist in weather modeling? Again, please ask questions when they arise. Don't feel like you need to wait for me to be done with this presentation to ask anything. Okay, so generally, how do we forecast weather? Weather forecasting actually starts with observations. So this graphic is really nice. It shows kind of all the ways that we can gather weather, but the main ones that we're going to be talking about are surface stations, weather balloons, satellites, radar, and aircraft and ships. So surface stations are great because you can have high density. You can have them in people's homes. You can have them in official locations. They're going to measure things like temperature, humidity, wind speed. They can measure air quality, solar radiation, a bunch of different variables that might be important to the atmosphere. Weather balloons are also a really essential observation. So that is this right here. It's called a radiosonde. These are important because they collect upper atmosphere data. So as weather modelers, we need to know not only what's going on at the surface, but what is happening aloft. I'm sure people have heard of the jet stream. The jet stream is a wind system that happens in the upper atmosphere. It's typically traveling it can travel in opposite directions to your surface wind. So if you've ever been in Hawaii and you see the trade wind cumulus clouds, the shallow clouds that exist on our mountains, they're traveling towards the southwest. But then you see some upper level clouds and they're traveling in the opposite direction. They're being carried by the jet. Then we also have things like satellites. These provide information on cloud cover, temperature profiles, and precipitation data, localized radar that exists within the radar network of the United States. And then sometimes we can get data from aircraft and ships. So I would say for weather modeling, weather balloons or radiosondes are our most significant source of data right now because they provide that upper air information. They can be lifted all the way into the stratosphere. And for those who don't know, the troposphere holds all of Earth's weather. So being able to observe the entire length of the troposphere is really important, which is approximately 30 miles high. It can transmit all of this data down to the ground immediately. So you have these in situ observations available. And right now we have over 90 locations in the United States that launch weather balloons, with most of the stations launching 2 times daily. Globally, we have 1,300 stations that participate in this effort. All of them are launching weather balloons at the exact same time, which is really cool. So when we launch in Hawaii, that means everywhere else around the globe is launching at the exact same time. And so we get these really nice vertical profiles of the atmosphere globally. So this is just an example of some of the weather stuff that we get in Hawaii, some of the things that contribute to the way that we can predict weather in Hawaii. We have our radiosonde data, which is 2 times daily at both Lihue and Hilo. This is a radiosonde. It's kind of ugly, but you have your temperature. I don't know if you can see oh yeah, okay. You have temperature and then dew point. This is your wind speed as well as direction. And then this is your pressure. It's a function of pressure or altitude, essentially. We also have a geostationary satellite that exists over Hawaii called GOES 18. And we have 4 NWS radars in Ho'ipu, Central Molokai, and North and South Big Island. So what is a weather model? Weather models are basically just advanced computer simulations that predict atmospheric conditions based on physical laws and observational data. They use mathematical equations to represent the behavior of air, water, and energy in the Earth's atmosphere. And these equations are solved over each grid point, with each grid cell representing a specific area over the atmosphere, both horizontally and vertically. Observations from what I just mentioned previously are integrated into the model to provide the initial conditions, and then the equations that we have solve with these initial conditions for further periods of time to help predict the weather in the future. Key components include things like temperature, pressure, wind, humidity, precipitation. And by running these simulations over different time frames and different spatial and time resolutions, weather models generate forecasts that range from short-term predictions to long-term climate projections. So you can see in this little depiction here, we not only have horizontal grid spacing, but we have vertical grid spacing. This is an example of a global weather model, but you can have weather models that exist on all scales, such as ones that only cover Hawaii or ones that only cover CONUS, the United States. So kind of a trade-off of things with the reason we don't just all run global climate models all the time is because, yeah, there is this big trade-off with regards to scale. So if you want to predict something like global warming, you need to be able to predict multiple centuries worth of weather. If you're going to do that at 1 meter resolution, you're never going to do it because it's going to be too computationally expensive. So typically you need to have quite large grid spaces of approximately 100 kilometers, which is very coarse. When you think about the scale of the Hawaiian Islands, like the Hawaiian Islands aren't even represented on that grid scale. So in climate models, a lot of the times the Hawaiian Islands aren't even represented. And then as you move into smaller scales, you can start representing smaller and smaller processes, things like cyclones or thunderstorms, or if you're getting really nitty gritty, you can represent things like dust devils when you have much smaller grid spacing. So I have this graph represented again because what I study are these processes. So most of the time, the things that I study aren't represented or they're not being directly numerically resolved in models at all. They're too tiny. When you think about a cloud, and the cloud community will talk about this, we talk about what happens in a cubic centimeter and the interactions that are happening in a cubic centimeter, which is so incredibly small when you're thinking about trying to model an atmosphere. So in order to get away from having to represent, or not even representing these processes, but representing them in larger models, we have these trade-offs between a resolved part of the model versus a parameterization of a model. So when something is resolved, that means it's explicitly numerically represented. This is going to be represented with things like partial differential equations. It's going to be solved computationally. It's very expensive to resolve things, but it's really important to resolve things like large-scale flow of the atmosphere, because those things dictate where we're going. We don't just want like a statistical representation of motion in the atmosphere. For parameterizations, though, which are much smaller processes, we can take more statistical representations of these processes and implement them, and then say, okay, to a first-order approximation, we can generate clouds in a global climate model, even though we're not specifically resolving those cubic centimeter processes. So that's the difference between being resolved and having a parameterization. So these are just some examples of the current numerical weather prediction models we have. I've taken both of the top images from this website called Windy. If you haven't been there already, it's an excellent resource. It has lots of, let's click on it because it's nice. Maybe some things you haven't known about it is you can actually change the model below. So NAM is the North American model. North America model only resolves, oh no, where did it go? Anyway, it only resolves North America, so like Alaska, CONUS, and Hawaii. But ECMWF, which is the European Center for Medium Range Weather Forecasting, and GFS, which is the Global Forecasting System, they are global weather models. They at different length scales. So you can explore stuff on that windy site, which is really cool. And if you want to get even more specific, you can go to PACIUS, which is a Hawaii-hosted weather site, where you can look at WRF runs for the Hawaiian Islands specifically. And this data, I think, is up to a 5-day forecast that's updated daily. The data is also saved on PACIUS, so if you want historical model runs, you can go access this there as well. But this is a higher resolution model. I think it's approximately 2 kilometers, which is pretty good. It helps resolve some of the things like topography and land use in Hawaii that are not represented on a global scale. Lastly, if you're interested in CONUS, there are WRF runs that NCAR does on the daily where you can go and get access to these as well. Okay, so now what is WRF? WRF stands for the Weather Research and Forecasting Model, and it's a state-of-the-art mesoscale numerical weather prediction system designed for both atmospheric research and operational forecasting applications. The model serves a wide range of meteorological applications across scales from tens of meters to thousands of kilometers. So it's very versatile. And right now it's currently a community-driven model, which means it's open source and there's a lot of community collaborators around the world working on this model. That's not to say that it's not validated though. Any updates that happen to the official model themselves go through lots of checks and balances to make sure that everything is going to come out in a way that's physically meaningful. However, because it's open source, that means you can try your own stuff in the model and see if it improves or doesn't improve the forecast. It's hosted by NCAR, so the National Center for Atmospheric Research, but it also has contributors from NOAA and ESRL and a bunch of other organizations, as well as people amongst universities in the US and overseas. Globally, these statistics are kind of old. As you can see, I've taken some of these slides from the existing NCAR WRF tutorial because I'm not reinventing the wheel here. There's tons of resources that exist for this, but I'm just trying to truncate it into an hour period of time. But globally, NCAR is used, or WRF is used in 184 countries, which is pretty cool. Just showing how implementable the system is. It's got a growing research base with about 50,000 users, and the US currently makes up the largest portion of those users at about 26%. But it's a globally recognized model with a growing user base. A majority of the people who are implementing WRF are in university settings, but it's also being implemented in government labs and private labs around the country and world. So I borrowed these PowerPoints, and so this information is just like a little old. Right now, they only have one dynamical core, and that's going to be the Advanced Research WRF, or the ARW model. The dynamical core is going to be the thing that dictates how all of our governing equations are explicitly represented in the model. It's going to resolve all of the important things like advection, which is just movement of wind, the Coriolis force, pressure gradients, buoyancy, all of these atmospheric processes, all of these fluid dynamic processes in the atmosphere. So in this case, when they refer to the core, they're referring to all the things that are partial differential equations. They don't really want people messing around with this stuff as much because it's kind of been well established, or the way that we currently represent it has been well established to work in the community. Again, it's all open source, so you can do whatever you'd like to it, but in general, they'd recommend not trying to screw with these governing equations. These are all primarily written in Fortran, which is a really old coding language, but it's very computationally efficient and especially compared to languages like Python, R, and MATLAB, or yeah, MATLAB, things that are more data visualization languages. But we're running into problems right now because a lot of the chip creators like NVIDIA, and I'm not into it that much, but NVIDIA doesn't want to continue to make GPUs and CPUs that maintain the ability to run Fortran. So there are some government labs in the United States right now that are trying to transition the WRF model into C++, so a more modern version of Fortran. So I keep mentioning that this is open source. So one way you can look at all this source code in a kind of nice way is going to their GitHub. I don't recommend trying to compile this on your own computer because the odds of you getting everything correct is probably slim unless you have a computer science background. So I would never do this myself. I would either look for a precompiled version or I would be talking to people at some of the big labs to see how you could do this. But it is here. If you do want to take a look through it, the directories are present, and it is technically downloadable if you'd like to have it on your own computer. What I would really recommend doing, though, is turning to HPCs that have support for WRF. So the two that come to mind are COA, which is the UH's supercomputer. It has a precompiled version of WRF, and then also NCAR's supercomputer, Derecho, which hosts a precompiled and a non-compiled version, which means that the source code is more customizable. I think requesting NCAR accounts right now are free if you're affiliated with the United States University. And as of right now, if you don't have an allocation, or basically if you don't have any hours on the Derecho supercomputer, you can also ask for a small allocation to give you some free hours there. But I will say an advantage of using COA is that the wall time, or basically how long you can run your model for, is 7 days. And on NCAR, it's only 12 hours. So if your model doesn't complete within that 12-hour run, there's ways you can get around that being not an issue, but it's just more cumbersome. It's nicer when you can just let your model go and not have to worry about checking on it every 12 hours to continue the run. But both of these are really great resources to start. And last but not least, I wanted to throw up the WRF tutorial that they offer. I think it's generally twice a year, but the next one that's coming up is in winter of 2025. It's remotely from February 3rd to February 7th, but unfortunately it is Mountain Standard Time, so you will have to be up at 6 in the morning with your thinking caps on, ready to talk about weather models. But I will say, as a participant many years ago, it was really useful for me to be a part of this. You have access to people who wrote some of the foundational code, who are in the models, who are doing model development, which is not a majority of the WRF community. A majority of the WRF community simply use the models, but are not actually part of the inner workings of it. So just being able to interact with these people, not in like an email format, but through Zoom, is really nice. And if you don't want to pay the $50 to $100 that it costs to go do that, and you want to do a more self-paced thing, you can do their online tutorial, which is pretty good as well. It has a few less things than the week-long tutorial, and you have a little bit less access to stuff. It's also more variable because this is not maintained as often, but it is a great place to start if you're looking to start using WRF for free. Okay, so now what can you even do with WRF? Why would you even want to bother doing this anyway? So it's a really powerful research tool. There's, you can do things like idealized simulations, which I'll talk about in a little bit, or you can experiment with real-time forecasting applications. So in this bottom image here, we have a cold front that's passing over the United States, which is this band, and in WRF, you're able to kind of truncate it into the different types of precipitation really easily because the model stores all the precipitation types separately. So you have rain, freezing rain, sleet, and snow. You can represent all of that really well, as opposed to just saying that there's precipitation there. Next, you can do things like you can integrate satellite data into WRF and then run it to understand which of these radar reflectivities are actually convective. Convective meaning like producing raindrops or are raining. And so here's an image of the satellite, and then they put it through WRF, and to figure out what was being convective or what was raining or not, you can see that these clouds over here were removed. So kind of interesting for that. Also, you can use it to simulate hurricanes at higher resolution. Global models are not going to be able to produce hurricanes at super high resolution. Oftentimes, when we feel like a hurricane is going to form, what happens is a sub-model is triggered in these global models that help to spin up the hurricanes. But in general, on a global scale, they cannot be represented well. So obviously, it's important for us to be able to run hurricanes at high resolution so that we can inform the public what's going to happen if there is one. And then lastly, you can do ensemble forecasting, which is really interesting. You can run multiple models of the same scenario. You can tweak a few things in the model to see if it changes the output. It's just a very powerful tool. So in general, to recap, you can also develop and test for physical parameterizations. So if you remember when we were talking about them, these are things on a subscale process that you can't actually be represented, which means right now we have a lot of parameterizations that they come from one study of cloud and aerosol interactions, and then they use that to represent the entire globe. And maybe you do a new study on cloud and aerosol interactions and you want to update this parameterization. You can do that with WRF, proof of concept that you've improved the model, and then move forward with publications, and then people use your model and you get a whole parameterization named after you, and yeah, all of that. So that's something that's really nice about it. You can use it to study specific weather events. So I'm from Buffalo, New York. We get a lot of lake effect snow. The year before I left for Hawaii, we got 2 meters of snow in 2 days. You can use WRF to understand the system, all of the mechanisms that contributed to that event. You can do regional climate studies, which are really interesting. You can couple it with some additional add-ons like chemistry, fire, and hydrological applications. You can assimilate data in real time. So WRF has been used for nowcasting, or which is the really short term future weather forecasting that integrates things like radar and satellite data. And then you can also use it as a teaching tool for modeling and numerical weather prediction. It also, is used for numerical weather prediction, so hindcasting, real-time forecasting, and then forecasting for things that are more industry related, like wind power, solar, and air quality. Okay, so there are two main things in WRF that you can run. You can run an idealized simulation, or you can run a real simulation. So an idealized simulation is going to be much simpler. I have this little image below. It's good for investigating a lot of the physical and dynamical properties of a system. It removes a lot of the complex variability that comes from the day-to-day weather modeling. But it's not really representative of any real day. But it's really useful because you can understand how, in general, in this case, for example, you have wind coming from the north side, wind coming from the south side, generating this region of convergence. When you have surface level wind that collides with each other, like mass continuity tells us that air must go up, so you create this region of convection. And so you can use it to study these like really interesting fundamental aspects of the atmosphere. And then on the flip side, you can use the real applications, which are a little bit more complicated to get into, but they're good for when you're trying to understand particular aspects of observed weather events, or if you're trying to forecast weather, if you're trying to compare between different weather events in different regions, days, etc. It's more, I would say real is probably the most used aspect of WRF, but ideal is also really cool. In your WRF directory, you're going to have, these are your bread and butter. Your real is one option, but then your ideal come with all of these sort of pre-loaded scenarios. And these are just going to set up the dynamics of your model in a way that feels meaningful. You can either choose a 3D model, a 2D model, or a 1D model. I would say if you're just getting into WRF, the one that's always been recommended to me is this EM Hill 2D. And it's essentially, it's not an actual 2D model, but it's a very long flume where you have wind traveling in and you have a mountain that's homogeneous in shape, just a little lump. And it's just a way for you to make sure that everything that you've set up in the model is working and accurate, because in atmospheric science, we know that we know what the weather, what the winds should look like in the lee of a mountain. And so you run this simplified model, you go, okay, am I getting what I'm supposed to be getting? And then you move on. But Ideal models are typically less computationally expensive. They're easier to learn. So if you're just getting started, I would start with one of the ideal runs. Okay, so now we're getting into like what actually goes into the WRF model. So what does WRF look like to a user? Unfortunately, there's no GUI or GUI, which stands for graphical user interface, but and a graphical user interface is just a nice interface that lets you touch buttons. And I will say this is not normally a priority of people who do atmospheric science, is to like make GUIs. So most of our models don't have them. The one model that I've used that does have one has a horrible GUI, so I would say we should just keep away from doing them at all because I'd rather just use the command line. But you're going to interact with WRF through the command line. And this is just like a little screenshot of what the directory looks like when you're in there. It's going to consist of subdirectories, files, and then executables. So now let's assume that you have WRF compiled somewhere, on Koa, on Derecho, on your own computer. This is the general schematic that you would follow to do this. And I'm going to break it down into a little bit of parts and also try to show you some of the resources that you can utilize for each step that will either tell you more about this model or tell you where to get the model or where to get the data from, or etc. Okay, so first and foremost, you need to choose whether or not you're trying to forecast or whether or not you're trying to use it to research weather. So let's assume you're using it for forecasting. You're going to need input data to start the model. And so you're going to choose either the alternative observation data or your conventional observation, and you're going to run this through the WRF preprocessing system. This WRF preprocessing system is like a foundational part of all of the real runs that we initiate. If you're taking alternative data, you're going to go to the WRF DA, which is going to be this user page. It's the data assimilation page. And this offers a freely available public domain with flexible state-of-the-art data assimilation. So you can basically take other models immediately and integrate it into your WRF run, which is really cool. You can use larger global models to force your smaller WRF run, which is great. And if you're using conventional data, you're going to use this ObsGrid program, which is also available on GitHub. I provided the links for all of these too, which I'm happy to share the PowerPoint with anyone who wants all of these links. The point of me adding these links is so that you can just click on them and use them. So yes, but yes.
Can you use the alternative?
That's a great question. I think I have to say I'm not a forecaster, but my understanding of the differences between this is how you create your input files. And so it's just the way you assimilate the data into the input file. But it would probably be, I would say if you did the alternative data, you'd probably lump this into there and take the alternative data route, whereas you wouldn't do both processes at the same time. But I am not an expert on that. And then, yeah, you're going to use the ObsGrid program if you're going to use the conventional data, which is already actually in WRF itself, but they have a whole separate GitHub that you can go and look at if you'd like. Okay, and now let's say you don't want to do forecasting at all. You want to use this for a research application, which means you don't really need a recent observation, or you don't need the models of the now to tell you what's happening, especially if you were looking at the 2015 snow event in Buffalo. Like, there's no weather data that's going to exist for that on any current modeling site. So where do you look for this historical data? My main experience is going through this on Derecho. So I would recommend using NCAR as a tool. It's called the NCAR Research Data Archive. They have tons and tons of different historical model runs that are used for different periods of time, different time resolutions, different spatial resolutions, which will all kind of affect the way that your model runs. So these are all things to consider. But there's a lot of existing data out there for your historical runs, both for CONUS and like globally. And if you want to narrow it down even further, I would click on the side here and do these support projects on the side, and you can explicitly click on WRF. And so WRF takes very specific files. They're called grid files, which is just the format in which the ARW core processes the input data. It's important to note, though, that simply converting your netcdf file to grid file doesn't guarantee that it's going to work in the WRF model. WRF is very particular. I don't know why, but they've been decommissioning some stuff lately that's been sort of frustrating. I don't know if anyone's familiar with ECMWF Era 5 reanalysis data. It's very high resolution, long period of time reanalysis data for the globe. WRF has stopped the integration of being able to use that as model forcing, which sucks because I really liked it. So I think it's a big loss, but if you use any of these currently WRF supported projects, they should work in your model. You can take data from somewhere else, but I cannot guarantee that it will work. And another small caveat is that maybe you've been able to take data from somewhere else and you've been able to run it through the WRF pre-processing system, and it seems like everything's going okay, and then you finally get to your model run and you put it in there and your model blows up. It might be you actually failed somewhere earlier, but because of the people who write this code, they don't write for infinite scenarios, so it might not have errored in a way that's obvious. And so I would highly recommend using the data that is currently supported. And if you want to venture off on the other stuff, be prepared to just be frustrated. But it's not impossible, but it's just a big undertaking. But if you pull from here, it should work. Okay, so you pulled your data for the weather aspect of the model, and now you need to give it some terrestrial data as well. This is going to be your topography and your land use, basically how much of your domain is city versus grassland versus barren rock. And this can be pulled from the WRF pre-processing system webpage, but WRF also comes with this predetermined, so if you don't actually want to touch this, it should be okay. But one thing I will mention is that if you have a really high resolution run, say 200 meters, and your topography level is 1 kilometer, you will have a really chunky topography in a high resolution model. It will not auto scale down. It will auto scale up for you, but it will not auto scale down. So that's just something to consider if you're trying to do a run that's, and I think most of the model resolution for WRF is 0.9 kilometers. So if you're trying to do any higher than that, you need to pull your own topography data. Okay, so now you have all your initial conditions, your observations, your historical reanalysis data, and you put it in your terrestrial data for your model. Now it's time to run it all through the WRF pre-processing system. In general, it's pretty straightforward. There's just 3 executable files you need. You need your geogrid, ungrib, and metgrid. Geogrid is going to gather all your terrestrial data and put it into a nice readable format by WRF. Ungrib is going to take all of your data, all of your reanalysis data or historical data, and to represent your initial conditions, and then put them into a file that's readable by metgrid. And then lastly, metgrid is going to chunk all of that information into a bunch of met files. It's going to be used to force your models. And this is just an attachment of the WPS directory from my personal directory. Yours should look pretty much the same. WPS typically exists outside of the WRF directory, like you download it separately, but it's pretty straightforward. And then this is really tiny, but you can see all of these homogeneous files here are your met files. So in this circumstance, I have the model being forced every 3 hours by reanalysis data. So every 3 hours, my model is going in and saying, what do we use next as our boundary conditions? How do we evolve from here? And what you would want to do at this point, when you have all your met files, is to transfer them to your WRF directory so then you can execute them. This is just a side note and also part of the chart. If you're doing ideal, you can skip everything I just said. So ideal doesn't require any of the pre-processing steps because it's just a run in an idealized model. The only thing that the idealized model takes as an input condition is a sounding. So the sounding is what we get from the weather balloons, which is nice and easy. And it's for this exact reason that I recommend doing ideal runs at first, get familiar with what you're doing before you're trying to go through all of these steps with potential error and then getting to the end and not having your model work. So this is just another schematic that I think sort of ties it together in a nice visual way. Your geogrid data is taking the physical land data. Your met data is being fed into the ungrib, and it's being decompressed in ways that it can then be read by the metgrid file. Then metgrid is taking everything, sticking it together. And then the last steps that you'll have here are to run your real executable file, which is the WRF model itself. And that's going to give you these input files. And you should check these before you run the next part. But once you do wrf.exe, your model's running. So lastly, once you're finished with all of your model runs, you're going to want to be able to post-process this data in a way. It just comes out as netcdf data, which is really great. You don't have to post-process it in a big way, but you'll obviously want to be able to visualize it, make sure that it did what you wanted it to do. There isn't any kind of weird model artifacts that exist, and etc. One of the most common ways that you can visualize this kind of on the spot, I don't know if this is a COA supported thing, but on Derecho it is, it's NCView. And NCView is a nice, easy program that allows you to instantaneously visualize netcdf programs. Unfortunately, this only works if you have a Mac or a Linux. I don't know why, but even if you're SSHing onto a Linux supercomputer from a Windows, it will not pop up. It's not a supported program for Windows, so that kind of stinks. But there's lots of existing programs out there that easy Python scripts that get you to be able to, visualize your data in a pretty straightforward, easy way. And this community is huge, so scouring the internet will provide you with lots of things that you don't have to write yourself. So maybe you're thinking, wow, all of these steps sound really easy. Or maybe you're not thinking it sounds really easy. I don't know. But one thing that I left out that's really important about all of these models is something called the namelist files. So there are nameless files for the WRF preprocessing system and the WRF, just the regular WRF system, either in your ideal or real run. So the WRF preprocessing system, the nameless file is going to consist of your start and end dates that you're running for. You're going to assign how many grids you want. So I'm not talking about it in this presentation, but you can nest grids if you want to get to higher resolution without immediately jumping from a very coarse climate model to a very high resolution, like 200-meter run for Hawaii. But you can have nesting. This is where you would set this. You set how many grid boxes you want in the X and Y plane. You set how many grid boxes you want in the Z plane. You set the dimensions. So this would be 25 kilometers. Pulling your geography data, this is where you're pulling it from. This is all in the WPS nameless file. And the real run also has a nameless file where you have essentially the same options, but also tons more. So this is where you're going to tell the model all of the different ways you want things to be parameterized. This will depend on what you're specifically trying to look at, whether that be if you're trying to look at clouds in really high resolution, or if you're, depending on your length scales, like once you get down to specific lengths, they can start resolving clouds. I would say at like 100 meters, you can start having clouds be resolved, which is cool. There's like hundreds of nameless parameters in here. And at this point, I would say you should hang out with a friend who does atmospheric science and works with WRF so that you can then determine what of these parameters is going to be best to work for you, because there's so many options. And in reality, these will really dictate how your model evolves. And so this is something that is where all of the other steps might be executable from like a monkey see, monkey do type standpoint, where you're like, I can type in this line of code and everything works the way I want it to, but the parameterizations are going to dictate how you interpret what's happened in your model. If you turn off clouds and then there's no clouds, you can't just say there's going to be no clouds in the future for climate. Like there's no clouds because you didn't put clouds in the model. So this is just something to consider. Okay, so that's the model basically in its entirety, the basic scaffolding of how you would run WRF. And then now I'm going to provide you with some WRF resources. So if you're interested in looking into this even more, they have all of these basically online user guides on the WRF users research page. They only have the version 4. I think we've pretty much moved away from version 3, which as of a few years ago, version 3 was still prevalent. But yeah, these are great. These web documentations look something like this, where they kind of break down all of the table of contents into different clickable web pages, or you can also see some of them have PDFs. which the PDF is nice because you can Command F when you're searching for specific things that you're not understanding in the model. But overall, WRF has really great documentation. This is not the case with other atmospheric models, but the WRF community has done a really good job with documenting how different things work. I'm just plugging again some tutorials. So in addition to the other two that I mentioned, WRF also has a using the Amazon Web Services WRF in the cloud type tutorial. I think this is free. You might need an instance with Amazon, but just something to look into if you're interested in trying to do this. Again, the WRF workshop, and then the free online one. I will provide these slides if people are interested. There's a WRF news email list. So if you're really into the modeling community, you can get this WRF news. It'll tell you all of the recent updates or bugs or things that are the community in and of itself is kind of struggling with. I'm in an iteration of this WRF news, and it's really nice to see, especially when the new model is released, people run into a lot of bugs very quickly, and it's nice to know that you're not the only one struggling. Also, there is this wonderful community forum provided by NCAR. I think you need to be a registered NCAR user, but I think it's also free to sign up. So, but this is literally a decade and a half worth of people asking questions about WRF stored in one place. And the same people who run the workshop that you pay to go to online are the same people who answer the questions in this forum. It's a wonderful community and it's extremely useful. And they can even ask, or they can even answer questions specifically about I'm having issues with compiling, things that are more computer oriented versus model oriented, but they're very helpful. And this is very much a direct line to the people who code WRF at NCAR. And if none of that stuff works, you can also search the internet. Like Stack Overflow has a bunch of stuff on WRF and coding and plotting in WRF. And yeah, so the community is huge. There's lots of resources available. And then next, I'm going to talk about a few extensions and customizations that might be more useful for your particular research applications. So for me, like I mentioned, I study aerosol. In WRF right now, there is a representation of aerosol, but it's very crude. It kind of treats aerosol as all one homogeneous group, when in reality, aerosol comes in all different types of flavors. We've got black carbon from smoke. We've got aerosol from biogenic stuff. We've got salt. We've got volcanic emissions. These are just natural aerosol, but then you also have smog. You have things from cities. There's tons and tons of stuff. And right now, the regular WRF model does not differentiate this stuff. So if you really want to get into how particular aerosol types are affecting cloud development or affecting the development of ozone or whatever, WRF Chem is your extension that you would use for that. They have a similar type community group online. This is hosted by Nanjing National University in China, and it's in collaboration with NOAA and ESRL. It's a great community. Lots and lots of people who are using WRF Chem. It's more niche, but it is great to know that there is an online center for you to come to with your questions. And lastly, like these are just some interesting applications of WRF Chem. So you can see the date up here. It's April 16th, the 3rd. You've got Saharan dust, a high concentration of Saharan dust. And then 2 days later, that Saharan dust is modeled to be moving over Europe. So this is good for human health applications, and the dust will also affect the way that clouds develop and therefore weather perpetuates in these regions. So our next one is called WRF Hydro. So WRF right now, it makes rain and then the rain hits the ground and that's it. So we want to be able to understand from a water resource management side, how is the output from WRF, how can that be used in a meaningful way to understand the longevity and the cycle of this water? And so WRF Hydro is kind of that. I know so much less about WRF Hydro, but I know that it needs to be improved for Hawaii because Hawaii has some very specific groundwater storage systems that are unique to the fact that we're volcanic islands, whereas most of the United States does not have this kind of subground stuff going on. But very cool, lots of cool stuff happening. I think it's happening here with Change Hawaii. There's Wharf Hydro. I meant to have a slide that kind of like showed all of the existing communities who are currently working on Wharf, but I didn't get to it. But you know, and you want to throw out names out at the end. Cairo is doing Wharf Hydro.
Yes.
Yes.
For the national water.
Perfect. Yes, and that's with Giuseppe Torre.
Giuseppe was on it, yes. Tom Luke, Tom Nevin,
Yes.
Eric,
And I think Allison Nugent too.
yes, Allison.
Yes. Perfect. Yes.
And
Yeah, Yingpan Song. Yeah, Wharf Hydro is very cool. There's still a lot of stuff being developed here. They have almost the exact same resources available, the user guides, the descriptions. I just wanted to provide these opportunities to show. And then, yeah, here's kind of like the general thing of what Wharf Hydro can do for you is it takes these fluxes of moisture and water and it puts them through the terrain that you have in your model, and it's important for water resource management. Is it existing as streamflow water? Is it existing as groundwater? Like where is it going? Which Wharf right now does not do on its own. And lastly, the third biggest extension you can have is Wharf S-Fire. So this is specifically useful for modeling forest fires. Forest fires, depending on the scale, create their own weather, which is it's fascinating, but really dangerous and highly unpredictable. And right now, we don't have any kind of stochastic variability in weather models to say, well, just randomly, let's just put a forest fire here. Like, we don't predict forest fires. We predict the likelihood of forest fires, but we have no way of predicting whether or not there will be a forest fire and to what magnitude that forest fire will exist. But this right now is a really interesting tool for us to be able to use from the research aspect, not the forecasting aspect, but we can go in, we can stick a fire in a geographic region, and we can figure out how it evolves. So this is something that you will have to download from GitHub, but it has on this website in particular a bunch of documentation on how you're supposed to compile this specifically. And here are some cool applications for S-Fire. So a lot of it is smoke plume evolution, but you can actually model ember movement and the dispersion of like heat and thermodynamics that are happening as a result of fire stuff. So this is from a postdoc in our department, Anastasios Robothikis, and he provided me this cool video of the smoke plume that he's been modeling. Okay, we're getting towards the end of the Wharf stuff. These are just a few final slides on some software and tools. So what I think is the most useful way to interact with Wharf is through Wharf Python, depending on whether or not you like R or MATLAB or whatever else you use for data visualization. That's up to you, but Wharf Python is a slew of scripts that people have put together to be able to visualize all of the Wharf output in ways that are meaningful to weather people. It's got awesome documentation. It's really easy to implement, and it's free again. And it's nice because it is open source. So if you find a bug, you can go on their GitHub and you can initiate a problem, or you can fix it yourself, or you can use it to make other cool things. It's very, very intuitive. And then the last thing is kind of this workaround that I mentioned. This is a workaround for the problem I mentioned earlier about not being able to use NCView with your Mac or with your Windows computers. So instead of using NCView, you can use this thing called Panoply or Panoply. Anyway, it's developed by NASA, and it's a really nice way to visualize NetCDF data like immediately. It will require you to download your Wharf data onto your own computer if you're using it on Koa or Derecho, the NCAR computer. But it is super easy to be able to visualize your data. You can click through the time steps, you can click through the vertical grids. It's really easy. So if you're looking to kind of just immediately verify that things are going well and you don't have access to NCView, I recommend Panoply. Okay, so lastly, I'm just going to wrap up some of the current challenges that we've had in weather modeling. Challenges that have historically existed and challenges that are currently that are existing today. So one of the largest problems that we have are data gaps. You can see generally over the regions of land. I mean, I will say these dots are huge. You have to remember this is one singular balloon at each dot. It's not like representing the geographic area of that dot. But over land, we've covered a fair amount. We could have better data representation in, say, Southern Ocean. Antarctica doesn't have that many. The Arctic does not have that much. Africa, South America, Australia is missing quite a bit. But our main problems are actually the open ocean. So if there are dots that exist in the ocean, it is because there is an island there. That island is willing to participate and launch these weather balloons. But when we don't have data from the open ocean, we're basically just interpolating in between them if we want to have initial conditions. And that's really bad, because there can be whole systems of weather that exist within these regions that aren't being represented at all. Satellites can help with that, so that's great, but satellites are a little bit more difficult to extrapolate the vertical profile like information that you get from the weather balloon itself. So, but I would say right now, data gaps are our biggest obstacle still to weather modeling. Next is kind of this like scalability. So talking about the resolving versus parameterizing things. The more you choose to resolve, the higher resolution you choose to get into a model, the more power you're going to consume, the longer it's going to take to run the model, the more cores you need. And so this is an interesting graph here showing that if you have, this is between a 50-member ensemble, which is just 50 model runs versus a single forecast. But regardless, as soon as you increase the model resolution, there's an exponential growth in how much power is demanded from these models. And something that is, this is just my opinion, but it's sort of speculative, but it's my understanding that computers have sort of reached the limit of our computational power. It's either this, what we have right now, or quantum computing. And we haven't made weather models into, they can't be used in quantum computers right now. But people are still kind of relying in the weather community on this improvement of computers to help us overcome these scaling issues, to overcome the computational costs. And in reality, I don't see it getting significantly better in the future. So we're going to have, this problem I think is going to exist for a while, which only emphasizes that we need better parameterizations in order to represent these important processes that are subscale. So going on to the small scale phenomena, a lot of extreme weather events happen on a smaller scale. These are things like microbursts, tornadoes, flash floods, things that are highly localized. They develop rapidly. They're not going to be represented in your average WRF domain. So this is a really cool, this system here is called Vapor, which is the model that they use to run this. Super cool representation of a tornado. You're probably never going to get a tornado to be represented in WRF. But small scale phenomena are particularly dangerous and they're really hard to predict. Right now, the way the National Weather Service does tornado awareness is by looking at radar data. And when they see this sort of hook that you can see someone's like drawn here, it looks like a fishing hook. You know that that is a tornado based on the radar coverage. And then you send out an alert, but we are not modeling tornadoes right now as a way of preventing public disaster. Another problem that we have is long-range forecasting. So overall, if you look from the years, forecasts have been getting better. 3-day forecasting is approaching 100% accuracy, so that's cool. But I mean, with 10-day forecasting, maybe we're at 50% right now. Things are getting better, but it's still something that is difficult for us to predict. You can imagine in any model, like errors start to snowball. So you have any kind of uncertainty, and that uncertainty snowballs as the model propagates. And interestingly, you can see the difference between the Northern Hemisphere and the Southern Hemisphere. So things are converging now, but I think for the historical problems, the data observations of the southern hemisphere were really, really sparse, especially because there's just less continental coverage in the southern hemisphere. And so now we've overcome that with some modern things, but I think that was what contributed to it being worse in the southern hemisphere than the northern hemisphere historically. Next is ensemble and probabilistic forecasting. So I don't necessarily say this is a bad thing. I'm glad that we do ensemble runs. So ensemble runs are, you have a hurricane that's forming here, you run a bunch of different models, tweak things a little bit maybe between them, and you're trying to figure out what's the probability of this TC forming or going where the models say it's going to go. And then you get these cones, which are generally NWS products or National Hurricane Center products that go out to the public so that you can predict where this hurricane is going to go in the coming days. But the biggest problem comes from not conveying this nuance to the public. And so I have a question here. What does 30% chance of rain mean? Who is bold enough to answer what? You go on your Apple thing and you say 30% chance of rain. What does it mean? Go ahead.
I have made this mistake many times, and I believe that 30% chance of rain means that in an area, 30% of that area will be getting rain on at the time. Is that correct?
Yeah, basically. It's like there's a 30% chance likelihood that somewhere in that forecasting area will get rain.
Okay.
And so, I mean, and we as like a weather community also need to be so much better than this, because I can tell you right now, I don't even know for Oahu what the forecasting area is. It could be the whole island, it could be just South Shore, like I have no idea. And that nuance matters when you're interpreting this information. So we need to be doing better as a community to convey some of these things to the general public amongst ourselves so that we understand what all of these graphs mean. Yes.
This might be an ignorant question, but how do you know what your forecasting area is?
I don't know. That's a great question. No, it's a great question. It's yeah, I don't think it's, and I will say, as someone in the weather community, I am horrible at keeping up with weather forecasts. Absolutely horrendous. I would not identify as a meteorologist by any means. I'm an atmospheric scientist. But I don't know. I'll look on NWS, the National Weather Service, and I'll see if they have anything that defines the geographic regions more explicitly. And I'll also check in with like KHON and the news forecaster things here to see if they have anything. But that's a great question, and I'll get back to you on that.
I have a forecaster Brandon, you can call him to.
Well, not to put him on the spot, but if Brandon wants to answer how we determine or what a forecast area is, you're welcome to check it in the chat or unmute yourself, whatever. But I also don't want to put you on the spot, so. But I'm happy to admit that I don't know how we determine these things.
Can you guys hear me?
Yes.
Yeah, so I'll try to make it somewhat clear here. But say you're in Waikiki, and you have a 30% chance of rain. What that means is, so it means that any point in that location, if you were to look at a map of Oahu, if you select a certain point on that island, that point would have a representative probability of precipitation or rain. Is it 30%? And that 30% would be in a 12-hour period, typically from 6 a.m. to 6 p.m. And how would you measure that? It would be, is there measurable rain in that entire 12-hour period? So measurable rain would be 0.01 inches. So I think the answer is, or the definition is slightly different than what was conveyed 3 to 5 minutes ago. It's that any point has a 30% chance of rain in that area.
How do you define the area?
It would be dependent on how the forecasters put those grids together. So you could have a very sharp gradient over the coalows that have higher pops. And then there would be a sharp gradient as you would head towards Waikiki in a typical kind of trade wind scenario. So it's more point based than area. And when you select that point and it spits out the forecast for that location, it's more that, not that 30% of the area. It's more any one location within that area would have a 30% chance of rain.
Do you know where
Confusing,
we get
huh?
Yeah, the nuance is always do you know where we get the area though? Like where would like NWS Honolulu tell us the area for their forecasting?
Yeah, so all of the forecasters are making gridded forecasts, and on our websites there's there'll be a map of Oahu or the Hawaiian Islands, and it's actually a point and click. So if you hover your cursor over a certain location and click on the map, it should spit out a forecast for that specific location. And so based on the gridded forecast that the forecaster put together, that would show the respective probability of precipitation or pops for that location for today, tonight, and so forth. I wish I could show some pictures here, but the fact that we're discussing this is it may be a great opportunity to try to put something like this together, just to visualize so that everyone's a little bit more understanding of what National Weather Service POPs means.
Yeah, I agree. I mean, I think I don't have a good grasp and I'm in the field. And I also would love to know, because in Hawaii specifically, the news forecasters, the news meteorologists don't need a background in atmospheric science. You don't need a degree to be a TV forecaster here. And that's not the same in other states of the United States. It's just state by state regulations. But I'd love to know how they use NWS forecasts and the nuance between what they're conveying to the public, whether it's the exact same thing that the NWS is doing, like up to the same standards, or whether they have their own way of talking about what 30% chance of rain is. Yes, Jason.
So I guess this question for both you and Brandon. Brandon's definition said anything that's greater than 0.01 inches, was it? So is there also predictions on how heavy, how much rain, what the volume of rain in just that percentage area?
Yeah, I mean, if you go to like the WRF forecasting for impact use and stuff, you can definitely see rain amount that's translated. I think it's harder though when you have like your little Apple weather map to be like, but I mean, Apple has also been doing some interesting AI stuff to integrate those forecasts into a more usable format based on your geographic location.
So if we think that it's too complicated to convey that to the public, so all we try to convey is if there's going to be potential flooding.
Well, I think the problem with like trying to pin down where rain is happening too is we're still not particularly good at that either. Like there are some regions where I think that, yeah, like you know that the Ko'olaus are going to get significantly more rain than Waikiki. That's just like a general situation. But as to whether or not it's going to happen in Kaneohe versus like Kailua versus Lanikai, like, and when it's going to happen, especially with our shallow, the normal white fluffy clouds, the trade wind cumulus that come by, like those precipitate sometimes and sometimes they don't. And so I think there's still a lot that needs to be done from a weather modeling standpoint. I think most weather modelers would agree. But But yeah, I mean, when you get into all of these, like when you get into all of the dimensionality of weather forecasting, you have to reduce it sometimes to suddenly get statistics for things and things that are easily conveyable. But in reducing all of that dimensionality, you then create nuance that maybe isn't conveyed as importantly as it should. Yeah.
I'm just thinking from a sort of practical reason, am I gonna get 30% chance of a drizzle or 30% of a giant torrent?
Well, I would say from a meteorological standpoint, we don't get microbursts here.
Right.
Well, maybe we do, but I've never seen a microburst here. But it's probably more representative of like your trade wind days, where it's like maybe you'll exist with some trade wind showers that come through, but in general, it's not going to be that much. If you have a 100% chance of rain, we probably have something like a Kona low or a cold front or something that's going to bring widespread rain, guaranteed, probably a little bit more torrential, but like, is a singular cumulus cloud going to dump 6 inches of rain on you? No. It's going to be a passing shower. Yeah. Good questions. Yeah, there's so much, like, we've been talking in our department about how there's so much, I mean, weather is something that is used by everyone daily, but we, as a community, still needed to be doing so much more to convey this information better, to inform the general public. And so it's always really interesting to have these discussions with people outside of weather, and even me being within weather and not understanding some of the nuance. So, okay, but I just have this slide. This is my last slide. So the last thing that's a difficult thing for weather is the impact of human and environmental factors. So climate change aside, you know, the fact that we're emitting greenhouse gases and that creates unpredictability in some of the systems that we have. Locally, you can have really interesting phenomena like the urban heat island effect. So here's just I don't know, like a Google Maps version of Louisville. You can see the industrialization, the whitish area, the cream colored, and the light green is more of the mountain grassland or mountain areas. Yeah. So then if you look at the heat map, you can see that there's this huge heat density that's focused in the cities, especially in the city centers. And these really localized dynamics will change the way that local weather forms and interacts with the big system, with the more synoptic scale meteorology or widespread system of weather. And this is not really utilized that well or it's not really conveyed in the weather models that we have, especially global models. It might be implemented in things like Hawaii's WRF because it's 2 kilometers, so it's much smaller. But I had also heard some interesting statistic that the presets for WRF right now have 0 industrialization for any of the Hawaiian Islands. So if you're running the presets for the land use of WRF for Hawaii, you don't have any city, which is crazy. So they've updated, other people have created data sets to upgrade this, but yeah. And that's it. That's my presentation. So I hope you had a good time. Yes.
Sorry, you could speak a little bit about WARP versus MPAS or MPAS.
Yes, so NCAR as an organization is moving towards MPAS. Let me see if I can pull up just to show you what. So MPAS is supposed to be this model for prediction across scales. It is a hexagonal grid point system, which is really interesting because it allows you to, I don't know if you can see in this image here, but you can do a whole global simulation and then you can zoom in really finely for things like the United States, which is a really neat way to get around some of the nesting tools that we have right now. MPAS is still very much in its developmental stage. So I will not be switching to MPAS right now because MPAS does not represent aerosol. So for my applications, it's not what I need it to be. But I do know that NCAR is funneling a majority of its resources into getting MPAS to be the model of the future.
And that variable mesh size is because there's more data over North America, so you can get a finer mesh, or?
This was preset in the model. So they said, we want North America to be represented at a higher resolution. And so you can do that within this. Whereas like traditional nesting is this, where you have very rigid boundaries. Yeah, you can see, you can zoom in. So you have your first domain, your second domain, your third domain. I know I'm not doing this justice right now, but every domain gets higher and higher in resolution, and it helps to represent some of these processes. Whereas if you were just to take a 2-kilometer like resolution for Oahu and then try to do that from a global climate model that's being run at 1 degree, which is 125 kilometers, you're gonna have really weird boundary conditions at those two model interfaces. And what MPAS kind of does is, instead of having these really harsh boundaries, you can scale the hexagons down a little bit more as it moves around this globe, which is cool. So you can deprioritize, you can still have a global climate model where you can have all these things running, but you can have really high resolution runs for, say, Kansas or Hawaii or wherever you want to. Yes.
Do you know if Anchor has any plans to develop a deep learning model for weather prediction?
What?
Deep learning model?
So that's a great question. I think NCAR is trying to prioritize using deep learning in ways like, we're talking about parameterizations. A lot of the parameterizations we have right now are just basic statistical models, or they're really simplified. They're really simplified math for the processes that are actually happening. But you can use deep learning to train a higher resolution model where these processes are being resolved, and then use the deep learning model to train on that, and then stick that in your big global climate model, so you don't have to use all of the computational resources to have this sub-process scale represented more accurately. I can't speak directly to NCAR's objectives, but I think a year ago we had the NCAR director come, and I think AI is it is something that NCAR is prioritizing, yes.
So I haven't kept track, but there's no like NCAR deep learning weather forecast model.
No. So the problem that I see with deep learning, maybe this will offend people, but is that AI does good for normal stuff, but it doesn't do good with extremes. And weather models don't do good with extremes either. So if you're training garbage, if you're putting garbage into your model, and then your model is representing that like garbage, it's never going to improve. There's still a lot of aspects to weather we don't understand from a physical standpoint. And we want to, the community is kind of torn because deep learning offers all of these cool outlets to rapidly not learn things, but rapidly represent these processes with less computational power and higher resolution and all of the benefits of deep learning. But we don't improve our understanding from a physical perspective necessarily. And as a result, we don't strengthen our overall understanding of what's happening in the atmosphere. And when you throw in things like climate change, and now the system is not acting in the same way that you've trained the deep learning model on, it can't evolve. Whereas from a physical standpoint, if temperature is increasing, it will change within the model in a way that is meaningful. I don't know if I'm answering your question.
I was just curious. Well, in the news stuff, there's all these things like Google has like a Google GraphCast weather forecast model. They get a plus of attention, but I haven't seen anything like from a research context like where we could like.
I think from an application standpoint, from like a consumable human application standpoint, there's tons of stuff that we could be doing with AI to make weather models cooler and more interactive for the public to be looking at. And this is just my personal opinion, so I don't speak for other people in the community. But as of right now, I think there's still a lot we need to do with making sure that our models are good before we start training deep learning models on them and thinking that they'll represent them as well. I think for aspects like downscaling and stuff, there's a lot of cool applications from that front, but yes. Yes. Did he? Oh, yes. Okay, cool. Brandon, you can unmute.
Yeah, I just wanted to follow up on what Katie shared there regarding machine learning models and deep learning at the government level. I just wanted to mention that it is a very active space. There's a lot of work being done on it, and it's all kind of experimental at this point. So things are not publicly available, but I can assure you there's a lot of work being done and testing to see how well things perform. And just a little bit of additional, it's the modeling stuff is a lot out of my wheelhouse, but as I have heard from some experts in the modeling world, these sort of hybrid models that incorporate dynamical aspects and the machine learning is kind of where a lot of research is kind of headed. So kind of hinting at what Katie was sharing with extremes, improving the dynamical side and more observations and seeing how best that can fit and mesh into the powerful aspects of deep learning and machine learning and all that. So yeah, I just wanted to add that real quick.
Yes.
What's a typical procedure for assessing the performance of the code? Like comparing against observations where.
Yeah, so I guess it depends on what you're doing specifically. If you wanted to duplicate, say like the example I gave with Buffalo, where you got a bunch of snow, you have ground measurements of snow, you could say, is the model actually, creating snow at the same amount? And if it isn't, why? And if it is, great. And we can move on to understanding more of the things about it. But do you have like a specific application that you're thinking?
I'm working on a project where we're trying to use deep learning to replicate the warp, but then. So what we consider a warp as ground, but warp itself is parameterized and there's some uncertainty there. We can't really measure the goodness based on the real situation because we're comparing against warp. So yeah, I guess I was wondering how, in the first place, how well, what's the procedure for even quantifying the goodness of the warp?
I would say from like a forecasting perspective, like it's kind of what you value. So like if you value precipitation in amount and location, like you could use either radar data to be like, where did it actually rain versus where did WRF predict it was going to rain? If you were trying to look at wind speeds, like is the WRF capturing like on like where all the wind turbines are? If you're trying to predict that, you can say like, well, what is WRF's predicted wind speed versus what are the wind speeds of these wind turbines actually observe? Like there's all sorts of ways you could validate it, and you could use all of them together if you wanted.
So it's gonna be right. Maybe just observations on a sparse location.
I would say observations would be considered more the ground truth. There's a lot of nuance to observations as well. Like if you stick a wind turbine, or if you stick an anemometer or something that's measuring wind right next to someone's house, it's going to be in a wind shadow, so it's not going to be representative of the wind patterns in that area. But if you stick it and it's like NWS sighted at 10 meters above this, like the land and whatever, like that would be a pretty good observation for wind. I would say that's it's like scientifically validated, and if you're looking for resources, like weather resources specifically, I can direct you to a few sites that use observations that I trust. So, and you can use them as just point observations to say, does my WRF model look like these few points? Obviously, we don't have grids of like all of Oahu, which would be great for like from an observational standpoint, but your group is working on kind of recreating some daily graded precipitation data based on observations based on some really interesting numerical ways to extrapolate in between these observations, as well as 10-meter wind speed, 2-meter wind speed, 10-meter wind speeds. So,
Then you're high,
yes,
250 meters.
yes, yeah, 10-meter high, U10 wind speed at 250 resolution. So that's like an interesting way you can validate whether or not WRF is doing what you want it to do. Yeah, it's kind of applications, but I'm happy to talk with you after it here.
Then you say,
Yeah.
yeah, okay. Yeah.
Yes. Are there any other questions? Yes.
I'll just already cover this, but I was curious, as far as being able to collect, real-time data from large expanses, middle of the ocean, right? Is there been an approach where, is it possible to collect data from, like, mass container ships or like all the shipping lanes?
That's a great question. I wish, as someone who studies aerosol in remote regions, I wish we could just put sensors on them. I think there gets into problems with like maintaining these instruments, which often costs a lot of money. And then like you're putting it into a private space where like, how do we collaborate with these private shipping containers from like I wish though, but there was a guy who came to UH a few years ago from NCAR. His name is Bill Coe. He's from NCAR. And he was talking about how we can use GPS satellites, which they kind of shoot out stuff at all angles, but sometimes they slice through the atmosphere in ways that creates very high horizontal resolution, and using this kind of remote sensing data to fill in all of these data gaps. But from these existing systems, like GPS is just up there for our satellites, or for our cell phones, for navigational systems. It's just an existing system, and a lot of that data is garbage for the GPS industry, but like maybe we can use it in a meaningful way based on some cool physics. Yeah.
So you mentioned PAC-IUS. The PAC-IUS is the Pacific Islands Ocean Observing System, and one of the sister organizations, the Alaska Ocean Observing System, is actually now working with the shipping industries to maintain in Alaska a bunch of vessel-based weather stations.
Awesome.
So they're trying to create a localized grid that can be fed into some of the local forecasting models, and we've begun some exploratory efforts. So with PAC-IUS, so we're looking into trying to figure out what it would look like to start implementing some vessel-based and more just weather stations on one of the islands, not specifically filling in some of the stationary gaps in addition to those mobile gaps. But yeah, that idea that we can start really painting the ocean with lines of more weather data is of big interest.
But that's great to hear. I mean, I would imagine like certainly there's value in that. It's for preservation of life and for safety reasons for humans on land, but also just like for commerce too. I would imagine it's Max's best interest to have
Absolutely.
the best data available for their projections too. So that's really great.
Modelers then have to figure out how to integrate the data, which
Yeah, and it becomes like observational data, which is my bread and butter. It's so like nuanced. Like sometimes you look at something and you're like, did that actually happen? Is that what they saw? And then you're like, oh no, someone sat on a sensor. I have like maybe I can find it right now. This great image. We have like the Hawaii Oceanographic Time Series here, Hawaii Ocean Time Series, and they have cruises every month. And I was using some of the data from the boat. It's the Station Aloha, yeah. I'm gonna stop sharing the screen and stuff and share the screen instead. But so this is a red-footed booby, and he's sitting on the wind vane and anemometer, because you can see the bird spikes on the rest of the boat. They've clearly armored it so that the birds don't sit on the boat or sit on the instruments, but he found his way up there, and he looks stationary right now, but he was going like this, and I was like, that is your wind direction data, and it is being dictated by this bird. And you know, overall, this is a nice. I think this is a Campbell. It's a young, so it's a branch of Campbell Weather Station, which is like a big national company that makes weather stations. But you would assume, oh, this instrument's got pretty good accuracy because it's fairly expensive and it's on this NSF research vessel, whatever. But I like went in and showed the captain, and she was like, "Oh yeah, he's up there all the time," and I was like, "Cool." So we yeah, it's garbage. It's not at least 100% accurate data for sure. So anyway, well, thank you all for coming, and I hope you have a good rest of your day. Happy Friday.
Thank you.